Welcome to a lesson with Dr. Powell. We're going to look at a special derivative of e to the x. But first, let's take a look at what e is. By definition, e is the number such that e to the h minus 1 over h as a limit equals 1. That's just how we define what e is. I mean, oftentimes things in mathematics are done by definition, by existence. So does there exist such a number, such as is equal to 1? That's another question to tackle, which we won't tackle right now. However, if we use that definition for e as being the thing that makes this work and tick, we get everything that we need from e here for derivative calculations. Let's play with this definition just a little bit. All right. Okay, let's think about this as a limit of an equation. And let's take that equation and play with it a little bit. E to the h minus 1 is equal to h. So we're still taking a limit of that equation. Now let's add 1 to both sides. So we have 1 plus h is equal to e to the h. And this is still limit of an equation. All right. As h goes to 0. And you should check it, right? E to the 0 is equal to 1 plus 0. You can just plug in even. Now let's take e to the e and raise both sides to the 1 over h. So if you raise both sides to 1 over h, look what happens here. 1 over h times 1 over h, those exponents cancel there in the multiplication, you get 1. So e is going to be equal to, and this again, this is a limit of this equation, 1 plus h to the 1 over h. So you could think of e as being the limit as h approaches 0, 1 plus h to the 1 over h. So saying that e is this magical number that makes this equal to 1 is actually equivalent to saying e is equal to this limit. So really, these ideas being equivalent, saying the idea, does there exist such a number, is the same idea as, does this limit exist? And this limit does exist. There are various ways of approaching that, which we won't tackle. But, for your sake, you could just plug in, you could just take arbitrarily small numbers and see that they do collide and eventually go someplace. And they go to this number e, and we just call e that limit. So we can actually compute e to very accurate decimal places by just picking h as small as we like in this particular computation. Okay, so that's what e is as a definition, and we can use it when we take derivatives. Let's see how we can use it. Okay, so let's take the derivative of e to the x. So to do that, we're going to put in x plus h and subtract e to the x. Put this all over h and take a limit as h approaches 0. Okay, what is this in the computation? All right. We can, well, if we think about e to the x plus h as really being e to the x times e to the h, notice how the exponents add. So this is fine. We can factor out minus 1 all over h. Now notice what we have here magically. This part, e by definition, makes this go to 1. Hence the limit. So hence, when we take this limit, we end up just getting, as h goes to 0, so notice how there's no h's, we just get e to the x. What? Let's use the derivative operator and practice using that notation. This means derivative. The derivative of e to the x is a function. I'm just writing it down as an expression, but we remember that this is representative of function y equals. But we just maybe don't write it, but that's what it refers to. So the derivative of this function, e to the x, is itself. Kind of nifty. So what does that mean? that means that if we were to pick a y value on the graph, maybe we pick the y value of 4, guess what the slope is right here of the tangent line? The slope would be 4. Kind of fun because you know exactly what the slope is per y value. So when the y value is equal to 100, the slope is 100. It's very steep. And so this is exponential growth. And notice how steep it gets. Thanks for watching.